All right, so that's what we have seen. Special families of non-compact groups, which are several different orthogonal and unitary groups of signature P, comma Q, and the symplectic groups. We have seen that they are matrix Lie groups, and we have seen they are non-compact, and we have seen their connectedness properties as well. So finally, I gave you some idea how to compute their Lie algebras. Now you just look at the Lie algebra, compute the dimension of the Lie algebra. That will give you the dimension of the respective Lie groups that you are considering. So that was a kind of that is kind of completeness of the example-based picture that I am trying to convey you since the last 11 and probably 11 and a half week. Okay, so that's all for this course. I do not think that I am going to work out many more examples at the moment. So please go through the material and try to absorb and understand the examples and the kind of methods that has been developed over the past weeks. So I hope you have we have done it by hand and have got something out of it. Now I still have one or two or a few, maybe some part of this week left. So what I will do from the next class, I will give you a very quick overview of the general theory of Lie groups. I would not say general theory, I will give you the general definition of Lie groups, how one can define, and then I will give you a very quick overview of the correspondence theorem between Lie groups and Lie algebras. So essentially, that is a combination of three main theorems in the theory of Lie groups, which gives you the Lie algebra, Lie group correspondence. We have seen it in our setup for normal subgroups and ideals of Lie algebras, but I will state the general kind of statement. After I briefly give you an idea how one define general Lie group, not necessarily matrix Lie group, but general Lie group in general, without referring to any group of matrices. And after that definition, all the matrix Lie groups come as nice examples, and they are known as classical Lie groups, and their Lie algebras are known as classical Lie algebras. Now there are some more non-classical example also, which we will not even touch upon. Okay, so all that for today. I see you in the next class with a very quick overview of the general definition for Lie groups and the correspondence between Lie groups and Lie algebras. Now, after that is over, I will try to give you some applications of Lie group in real life. So, thank you very much. Okay, so after the generalized orthogonal groups or orthogonal groups of signature P, Q, which are isometries of symmetric bilinear forms, in this lecture we will be studying isometries of the skew symmetric bilinear form. So we will consider K to be R or C. Then the symplectic group So it is called symplectic because it is it preserves the symplectic form. The symplectic group sp2nk I define in terms of matrix notation, that is GL2nk, such that A transpose JNA equal to JN, where Jn is the skew symmetric matrix, this. Okay, so we will consider this group, and these are the matrices that comes from a skew symmetric bilinear form. Okay, so again we have to refer to linear algebra for that, and it's a classical result of linear algebra that you take, just like you have any two symmetric bilinear forms which are characterized by this signature P, Q, symmetric non-degenerate bilinear form that is characterized by the signature. Similarly, you have any Q-symmetric bilinear form that will be up to equivalence of this form. So this corresponds to the symplectic or skew symmetric non-degenerate bilinear form on Kn. Now, up to equivalence, there is a unique such bilinear form. So this is given by Bxy is X transpose Jny. So that is, if you break it, Xi equal to 1 to 2n, and actually you can also prove that on odd dimensional vector spaces there is no skew symmetric form. So skew symmetric form appears only on even dimensional vector spaces over Kn, and up to equivalence there is this unique one which is given by this. Okay, so this is Xi y n plus I minus x n plus I yi, and this will be I equal to 1 to n. Okay. So this is non-degenerate and symmetric. Non-degenerate, yes. All right. And if you can define sp2n. So sp2nk is A in GL2nk such that Baxay equal to Bxy for all xy equal to K2n. So which preserve this bilinear form. So in matrix notation, this is star. Okay, they are the equivalent. Okay, so they are equivalent, the star and this. Okay, So now this is what symplectic group is, the definition of symplectic group. Now we want to understand whether it is connected or compact, and also whether it is a Lie subgroup. That's also what, I mean, it is not very difficult to see, just like earlier, that sp2nk is a matrix Lie group. Okay, it will follow similarly. Now we want to test the connectedness and compactness. I think more than compactness, especially we are interested in connectedness. Compactness will follow along the way. Now to do that, we want to understand some linear algebraic properties of this group. So first of all, observe that if A in sp2nk, then A transpose is Jn A inverse Jn, A inverse is minus Jn A transpose Jn. In particular, both A transpose and An belongs to sp2nk. So, in particular, A transpose belongs to sp2nk, and A inverse of course belongs to, and you can actually also use this fact to prove that sp2nk is a group. Just abstract group. I mean, there also you can use these formulas to prove that. Okay, and it has also very nice properties that if you take you take any matrix from sp2nk, then so note, you see sp2nk is contained in SL2nk. To prove this, observe that if Px is the characteristic polynomial for A in sp2nk, then Px is determinant A minus xi2n. By definition, that is same as determinant of A transpose minus xi2n, which is same as determinant A transpose. You already know the formula for the A transpose. Okay. Yeah. Now I2n is what? I2n is the identity. So identity is same as Jn. So this form, this is actually, so Jn square is minus identity, right? So you can write it as use that to write it as determinant minus A inverse plus X I2n. Okay, so this is same as determinant of A inverse, then you have x to the power 2n, and you have determinant of minus 1 over x I2n plus A. Now, what is determinant of A inverse? What is determinant of A inverse here? Okay, determinant of A inverse, yeah, so this actually we are getting here lambda. Okay, so actually you just take one step here. So this is determinant A inverse, and it will be a determinant, minus I2n plus XA. So determinant A inverse x2n, determinant A, take out A here, and this will be determinant okay, there is just a minute, so let's see. There is some calculation here. Just give me. Let's do it. Okay. So this is actually then determinant A inverse into determinant minus I2n plus XA. So determinant A inverse, you take x out, x to the power 2n, determinant A minus 1 by x I2n, which is, so we have what? A transpose JNA equal to Jn. That means determinant A square equal to 1. So determinant A inverse is plus minus 1 x to the power 2n, and that is P 1 over x. Okay. So in other words, Px, the characteristic polynomial, is plus minus x to the power 2n P 1 over x. So for every eigenvalue lambda, so thus for every eigenvalue lambda, this implies P1 by lambda equal to 0. That is 1 by lambda is an eigenvalue. That means SP2nk is a subgroup of SL2nc. Okay, and you can prove easily that SP2k is same as SL2c. Okay, SP2k is same as SL2c. And now we know, right, that every SP2, so SP2k you can always get a copy of SP closed subgroup inside sp2nk, and we know this is not compact. So sp2nk is not compact for n greater than equal to 1. So non-compactness is clear. Okay. And of course, I mean, this is a proper subgroup. Okay. This is a proper subgroup. You take all this real diagonal matrix, they does not belong. You can always find out one element in SL2NC which is not symplectic. It does not preserve. And, for example, you take the orthogonal matrices that we have seen. They are also subgroup of SL2 and C. But which matrices can simultaneously preserve both symmetric bilinear and skew symmetric bilinear form? Not all, right? So this is a proper subgroup. Now we want to test the connectedness. Okay, and of course, this is a closed non-compact subgroup. Okay, so now let's try to. Okay, so when I say sp2k is contained in sp2nk, that means it contains a copy of sp2nk. It's not a proper inclusion in that sense. Okay, but you can always take these matrices, for example, and 1 1, where A is from sp2k. Okay, so this is actually, I identify with sp2k, and that's what I mean when I say it is a subgroup. It is contained in sp2n, k. All right. So now, to prove connectedness, we want to use another result from linear algebra. Now, so we will follow. We will use a result about generation of symplectic group. Now, for that, I define. Okay, so for u in k2n and lambda in k, define the map t u lambda k2n to k2n, which maps v to v plus lambda b v u u. Okay, then take w to be those vectors which are orthogonal to v. All right. Then t restricted to w is identity, and tv minus v belongs to w for all v in v. Okay, so these are like reflections of the Euclidean plane, and you can check that they preserve the symplectic form. Okay, so they preserve the symplectic form. One can check that what is the dimension of this thing. So dimension of W will be 2n minus 1. Okay, so these are hyperplanes. All right, so these are so TV minus V is in V, right? TV minus V belongs to W, where I am taking B. Yeah, so U belongs to W. So because it's a symplectic form, DE is 0, so it belongs to W, which is a non-empty subset, right? So that means so T U lambda is a symplectic linear map, hence an element of SP2nk. So here we have used identification of a linear map which is matrix. Now a classical result SP2nk is generated by maps of the form Tu lambda called transvections. Okay, so they are generated by such maps. So now claim SP2nk is path connected. So take A in SP2nk, then A is a finite product of transvections. And now if you can show that every transvection, so it is enough to show that Tu lambda is connected to identity for U in K2n lambda in K. Okay, then we are done. And non-zero U. I mean, that is the assumption that you have to make here. So for 0 not equal to U. Okay. Now this is the ED. Okay. So define gamma 01 to SP2nk by gamma T is Tu 1 minus T lambda. 1 minus T lambda. Okay. Then gamma is a path joining Tu lambda to identity. Okay, so gamma is a path. So when gamma 0, it is so gamma is a path joining Tu lambda to identity. Hence SP2nk is path connected. Okay, so now we earlier we have seen SPN, which was the unitary group over quaternions. Now, it's a small exercise. You can see that this compact group is precisely the intersection of sp2nc and u2n. Okay, so you embed spn inside gl2nc, spn into gl2nc, then all the matrices that corresponds to spn, they will be in this intersection. Okay, and we have already seen that this is compact and path connected, but this is non-compact, sp2nk. This is non-compact and path connected. So we have already seen these non-compact groups. Now, what are the dimensions of this group? For that reason, you have to compute the Lie algebra. So what is sp2nc? So sometimes even here in this lecture I use this notation sp2n, but in the literature these groups are also denoted by, I think that is more common notation, as SPNC. Okay, and the Lie algebra for SPNK. Okay, and the Lie algebra for this group, one has to see what is the Lie algebra. So the Lie algebra is obtained as the following, that this, you take all G in the Lie algebra of special linear group, and here what they satisfy? They satisfy A transpose J2n A equal to 0. Now a crude rule, you replace, equal to J2n, right? So in the orthogonal group, the rule was you replace product by identity. Okay, so that gives you the Lie algebra, right? So here a crude rule, you replace this product by, so you have A transpose J2n A J2n, A transpose J2n, yeah, right? So this is J2n inverse, that is minus A J2n, right? So that means, and then minus A J2n equal to identity. So what you do here, you replace product by identity, and you can guess what is the Lie algebra here. The Lie algebra will be G transpose J2n plus J2ng equal to 0. And you have seen OPQ. And what is OPQ? That is again P plus Q R, and this is G transpose IPQ plus IPQG equal to 0. So here you have A transpose IPQA is IPQ, right? So A transpose IPQ is IPQ A inverse. So you just sort of add one plus here. Instead of equality, you add plus there and replace A inverse by minus A. So that's the kind of crude mnemonic rule to remember the Lie algebras. Similarly, one can see what is SUPQ, SPPQ. So I don't want to give you the detail of all these things, because you can solve them as exercises as well, using the same kind of ideas that we have seen earlier. Now, one final remark, that this group sp2n, c is more than connected. It is simply connected. That means you take any loop that can be shrunk to a point that we have already seen. We will not see the proof, but they are simply connected and connected. But the real symplectic groups, they are only connected. They are not simply connected. Now, finally, I just want to give you some hints how these Lie algebras are obtained. You see, you have A transpose IPQ A equal to IPQ. All right. So that means you can actually take IPQ inverse A transpose IPQ equal to A inverse. So you have a conjugation here. Okay. And then if you take X belongs to M and R, and X belongs to M and R, then e to the power Tx belongs to OPQ if and only if G e to the power Tx transpose Tx transpose G is e to the power this is same as e to the power T G X transpose G is equal to the power minus Tx. So this condition holds for all real T, so that would imply that G X to the power transpose G has to be minus X. So this gives you this Lie algebra. Similarly, you can do it for Sp n, k as well. Okay. So just do it as an exercise, and that will give you this Lie algebra. And similarly, you can obtain these two Lie algebras as well, corresponding to the unitary and quaternary unitary groups of signature P, Q.